Hello everyone, welcome back to my channel. So in this video we'll try to learn the Cauchy-Schwarz inequality. So there is a very famous inequality and it can be used in many problems while solving inequalities. So before giving the statement of the Cauchy-Schwarz inequality, so we'll see a inequality before that. So suppose you have four real numbers A, B, C, D. Then if I take AC plus BD and square it, I have A square C square plus 2i's ABCD and B square D square. Now this I can replace, or we can upper bound it by A square D square plus so the middle two terms I have introduced it. So this you can easily see that it is true, because if I take A square D square minus 2ABCD plus B square C square, so this is nothing but AD minus BC whole square, which is always non-negative. So that's why we can replace that. So now here you can see that it is nothing but so if I now take square root, so then mod of this is less than equals to root over of times root over of C square plus D square. So this is the most simple case of Cauchy-Schwarz inequality. So in fact geometrically what does it signifies? So suppose you have two vectors. Suppose v1 is one vector whose coordinates in R2 AB and v2 you have CD. Then if you take the dot product v1 dot v2, so this is nothing but AC plus BD, right? And on the other hand, this dot product you have another formula that it is modulus of v1 times modulus of v2 and cos the angle between them, cos of theta, that is the angle between v1 and v2. So right, so now modulus of v1 I know that is root over of, because we are taking the Euclidean, the usual modulus thing, and then C square D square cos theta. But the thing is the value of the cos theta is maximum value is 1, so hence so geometrically also we can verify this one. Right, so this is the most easiest case of the Cauchy inequality, where there is two terms in two dimension we are doing. So now actually we can generalize this Cauchy inequality. So let me give you the statement. So suppose you have two sets of real number, each containing same amount of element. So suppose a1 a2 up to an, and you have another set b1 b2 up to bn. So be any two sets of real numbers. Then summation j equals to 1 to n aj bj, this modulus is less than equals to summation j equals to 1 to n aj square power half j equals to 1 to n bj square whole power half. This you can see that easily that it is the generalization, and equality holds if and only if so there exists lambda, that is a constant, such that aj equals to lambda bj, and this is true for all 1 less than equals to j less than equals to n. Right. So this is the statement. I think the statement is clear. So let us try to prove it. So we'll denote these quantities by some name so that it is easier for us to prove it. So let us denote a capital A to B, the summation of A's part, aj square, and B is nothing but summation j equals to 1 to n bj square, and C is nothing but product of aj bj. Now the inequality that you have to prove is, so if I square both sides, so C square is less than equals to AB. So if I can prove this, then we are done. So suppose B is 0, that is each of the quantity. So this implies that Bj has to be 0 for all j. So, and this implies that C has to be also 0, and the inequality holds, right? So we'll assume without loss of generality that B is not equals to 0. Now since B is sum of squares, B has to be positive, and hence, so now if I take this particular summation, j equals to 1 to n baj minus c bj whole square, this is always greater than equals to 0, and if I expand it, b square summation j equals to 1 to n aj square plus c square summation j equals to 1 bj square minus 2 bc, the product. So j equals to 1 to n aj bj. So now, but this part is nothing but A, and this part is nothing but B, and this part is nothing but C. So what we actually have is AB square plus BC square minus 2BC square. So now from each term, so 2BC square and BC square, here we can simplify, and we can, if we take a common B, then AB minus BC, sorry, C square. So since B is positive, so we must have AB minus C square greater than equals to 0, and our required thing follows. So C square is less than equals to AB. Now the thing is, when will equality hold? So the equality will hold when this part is equals to 0, and that means that individually each term has to be 0 inside the bracket. So equality holds if and only if Baj minus Cbj, so that is 0 for all j. And this implies lambda is, if I take lambda C by B, then we are done. Then Aj equals to lambda Bj. So I think this more or less proves the thing. So this proves the Cauchy-Schwarz inequality. Right. So once you have done this, so let us see one application. So this is a nice example. So suppose you have three positive real numbers. Then prove that a by b whole square plus b by c whole square c by a whole square, the sum is greater than or equals to a by c, c by b plus b by e. Right. So now we have to, the main idea, if I want to apply the Cauchy-Schwarz inequality, then I have to identify these two sets and then apply the inequality, right? So here we have some square terms, so that is getting matched with these quantities. But on the other side, I have to express these as some product. I have to find this ai or aj and bj, right? So let us see. So what I can do is, so if I start with the right hand side, because that will be the left hand side of the Cauchy-Schwarz inequality. So if I can multiply up and down by b here, up and down by a here, and up and down by c here. So then I have a by b times b by c plus c by a times a by b plus b by c times c by a. Right. Now if we apply the Cauchy-Schwarz inequality, so consider the sets. So we take the first element from each of them, and the second one is b by c, c by a, and a by b. Then what we have is now using the Cauchy-Schwarz inequality, we have a by c plus c by b. This is less than or equals to the whole square, right? So a square by b square by c square plus, so this power half times but you can see that these two are nothing but the same quantity, only they are rearrangement of each other. So this is nothing but equals to right. So this gives us the recovery inequality what you wanted to prove. So yes, so the main idea in Cauchy-Schwarz inequality is to identify what is the set you have to choose. So these two sets mainly you have to identify, or in fact these two, in general case you have to identify these two sets. Okay. So I hope this video was useful, and you can like the video and subscribe to the channel for more such interesting videos. Thank you.